now it's time to go to the transmitter sites with Alexander Kurz from GatesAir. So the stage is yours. Here's the clicker.
Thank you very much. Good morning, everybody. It's always a bad slot to be between you and lunch, so I try to be on time. So what I'm going to talk about is different methods how to keep a transmitter site alive and reliably outputting a signal. Of course, the head end, the contribution is important, and then later on, how to make the antenna resilient is also important for the system. The first thing is the transmitter itself. So we can build a transmitter in a way that it will come with multiple exciters. So redundant exciters allow you to switch between the exciters and have them, for example, on two different phases of your electrical power supply, or to connect one to an uninterruptible power supply. I'll talk about that a little bit later. The redundant modulators can handle various inputs. So most modern DAB signals or systems are built with EDI. So ETI is more or less on the way out. There is still legacy SDH networks, ATM networks in use, but components are hard to get, and most customers are switching either MPLS or satellite or other IP-based solutions. So it's becoming EDI is predominant. Also important is for the synchronization purposes, you have to synchronize the transmitters with a satellite signal or with an accurate time using either external or internal receivers. For reliability reasons, we recommend using the internal receivers because then every exciter has its own receiver, is connected to the satellite. Now, the transmitters itself, you can use various technologies to make them robust against individual failures or problems. So the first thing is to use multiple power amplifiers. So transmitters always consist of what's called an exciter, basically changing the EDI signal into radio frequency signal, and then power amplifiers that amplify the signal and combine the signal. You have multiple power amplifiers that allows you to have an uninterrupted signal even if one of them fails. Now, I'll go a little bit more detail into the power amplifier design itself, because the way how they are designed, I wouldn't say excludes, but minimizes the risk of a failure of a complete power amplifier block. They are typically made in a way that they are hot swappable. So you can take the complete power amplifier out and replace it with a spare part and are at full power very quickly. The load sharing that's written here means if you have a higher power transmitter, you typically have various phases of the electrical network going to various power amplifiers. So each power amplifier is connected to a different phase. So if you have a problem with your electrical grid, or if one system goes down, it doesn't affect the complete system. The power supplies, the way how we build it is you have 3 power supplies in the system. 2 of them are good enough to keep the system up and running at full power, as it's shown on the right side. And even if two phases or 2 power supplies fail, you're still not off air. You're still transmitting at 50% of power. At the same time, this allows you to keep running and avoid downtimes or reduction in service coverage, which may be requested by your SLA. What else how else can you design redundancy into the system? For example, the cooling system. One of the common parts that are failing are fans, because they run 24 hours, 365 days a year in a sometimes not so clean environment. So you have dust, you have pollen from the trees outside, the fans are failing. So what we do is basically we do two fans for one component. If one of them fails, the other one will take over the load. This has two advantages. One is very clear. They run at lower speeds at the same time, which reduces the wear and tear of those fans. On the other hand, you're not interrupting your service. A similar design is with the pallets. The pallets that you see behind me, there is a IPA, which is typically a low power amplifier, and then you have 7 power amplifiers. Each of these power amplifiers has its own transistor system. It's a Doherty system, but they are individual. The advantage here is you have a failure on one transistor. The others are still operating at full power. And in some cases, if you're not running the power amplifier at full power, you don't even see it from the outside because the others are going to take over. Now, and if you need to repair them, you only have to replace one pallet, not the complete board. So there are designs that have massive boards with multiple transistors on it. If one of the transistors burns, and that's literal. Burning of a transistor basically means it destroys not only the transistor, but also the PCB layer, the board underneath it. You need to exchange the complete thing. So this is an important design matter. And let's say it this way, we do it, other companies do it as well. So, but you as a planning for the design should look into these details. AC redundancy. I mentioned the AC redundancy. If you have a higher power transmitter, it's very recommended to use a 3-phase connection. If you have a medium power transmitter, also 3 phases have an advantage because they are addressing different components in the transistor. They give you a better load, a cleaner electrical system, a better load factor. And I mean, it's listed here, the infrastructure cost. So the wiring that you need for a single phase versus the wiring for a 3-phase is different. The circuit breakers are different. But what I see, the important thing is the enhanced reliability and the scalability, because the 3-phase system in general allows you to be more flexible how to run it. Now, I know from some sites, and I'm looking at you, that some sites are single phase only. So depending on the site, you may have limitations in how to deploy that. Another thing in the power supply is how you buffer short outages of your grid connection. So if it's a few seconds or a few minutes, what is recommended is to either have an internal buffer, so a battery that drives the exciter for a couple minutes, an external buffer, a UPS system that drives either the exciters and key components for the time it takes for the generator to take over, if you have an external generator, or to buffer until power comes back. Now, why is it important to run an internal battery? For single frequency networks, you have satellite connections, and those satellite connections typically take anything between 5 and 10 minutes, I think, to connect to the satellites again. And to avoid such a dropout in a very short event, we and some other companies have internal batteries that just power up the GNSS, the satellite connection, for that amount of time. So for example, if you have a glitch in the network, it doesn't go down, so it keeps running. The next level of looking at is how do you make a system redundant? And we heard from Lars and from Wolfgang about redundancy on the head end. The same principle applies for transmitters. You can go with a 1+1 system redundancy. It's the maximum redundancy. You basically copy two identical transmitters typically in one rack, and you switch between them. It allows you to not only have one transmitter running at the time, but you can test with the other one. Typically, you connect the reserve transmitter, the one that's not active, to a dummy load. So you can simulate, you can run it up to power, you can load a new software, try out if it works for your use case. And the energy efficiency, well, they are very efficient in standby operation, I have to say. What else is here? Okay, now how does it look like? You basically have two individual transmitters connected to a switch and a controller. The controller monitors both transmitters and switches between them as needed, and you can do that manually or automatic. You can define how the switch back is. So you want to avoid a hysteresis or a toggling between the two transmitters if there is a problem outside, and then the system switches back and forth all the time. So you say, okay, you switch to the reserve and stay there until you manually switch back. And a manual switchback means somebody in your network control center says, oh, the transmitter is offline. What's happening? Aha, switch back. It's not necessary to go there, of course. And then the switch, the coaxial switch, typically connects one transmitter to the main antenna and the other transmitter to the dummy load for testing. Right button. Now, if you have multiple transmitters, you can extend this to what we call N+1. So if you have 3 multiplexes, then you can have a 3+1 system. It's not the same level of redundancy as a 1+1, but obviously it's much more cost effective. In other words, it's cheaper. The N+1 transmitter needs to know what to do in case it's called upon. So you have to tell it, well, you're now on that frequency with that output power, with that input parameters, and so on and so on. It is, as I said, it's cost effective. And yeah, the monitoring system talks to each transmitter, and depending on the failure, the failed transmitter gets connected to the dummy load for diagnosis and testing, and the reserve transmitter goes live on the air to the combiner, the main antenna. That multi-system controller is controlling the individual transmitters. It can be a 1+1, it can be an N+1. We also have a special variant, what we call a dual transmitter. It's basically 2 individual transmitters, and in regular operation, they are combined, and the combined power goes to the antenna. But if one of them fails, it gets switched off, and only the remaining transmitter goes on the antenna. That's basically -3 dB, right? If you have a regular combiner and one system fails, you have a -6 dB, because that's the way how combiners work. So the trick with a dual tran is you double the output power. It automatically diagnoses the connected devices, and that not only affects the transmitters, the system controller can also monitor other devices via, what's it called? The locking. And then interface, yeah, we have multiple variants of interfaces. Our controllers are typically optimized for GatesAir products, but we have mixed environments as well, where we talk with a GPIO to third-party products. So they're telling us power is off, power is on, activate the other transmitter, and so on. What we also can do, and this goes to the next level, is we can drive multiple antennas. So you not only have 2 different transmitters, but we can also switch to multiple antennas. Now, different to the automated switching for the transmitter switch typically goes automatic. Antenna switching is always manual. Main reason is if you have a environment, for example, here in Switzerland, where you have ice on the antenna, might impact the antenna characteristics. System diagnoses, oh, I have to switch. It tells the operator, and then the operator decides manually if or not to switch. Now, I do have one customer in the Middle East who has main and backup towers, and they are close, but they are not physically that close. So if one of them is impacted, they can switch to the other tower. System redundancy, I think I already spoke about most of these things. What is nice is you have a graphical user interface that makes it very easy to diagnose which system is on air, how to set it up. You're optimizing your uptime by having at least 3 transmitters on air in a 3+1 system. You can prioritize, by the way. I think one of you mentioned it. So if you have multiple transmitters failing, you can tell which one I want to be on the reserve transmitter. So for example, if you got 3 or 4 multiplexes, like a national multiplex, a regional, and 2 local multiplexes, you can guess the priority is first national needs to be in air, then the regional, then the local ones. This one. The final part of my presentation talks about the input redundancy, and you guys from 2WCOM have been presenting this really nice, so I'll make it short. What we do in this context is we have similar solution, server-based distribution from the head end to the transmitters, either multicast or unicast, using SRT, as you mentioned before. Our multi-streaming, we call it dynamic stream splicing. It's a similar technology where we send out 2 signals on 2 networks, maybe one on fiber, the other one on a backup network, combining the signal. This is widely used for audio distribution. For DAB, it's not that often, so that crown goes to 2WCOM. And what we also support is multiple headends. So the transmitters have the capability connecting to 2 different servers. So if the headend has a main and a backup server, we can identify to which networks to connect. And using the Intraplex technology, we can then use multiple wide area networks to not really eliminate, but reduce the risk of network downtime in between. That's it from my side.